Modern game development is all about game engines and hardware acceleration. If you go online and you ask a question like, how do I draw pixels to the screen? The answer you're going to get back is, you don't want to. That's true for AAA developers, where those games are so full of bloat that you cannot make them without hardware acceleration. But for somebody just starting out, the hobbyist, or for somebody who says, no, I really do want precise control over my pixels, that answer can be very frustrating. That older style of graphics is called software rendering, and is usually considered hopelessly outdated. So let's do it. Our modern computers are so fast and so powerful that if we're trying to make a simple game like Pong or anything from the 8-bit era, it's not going to be the software rendering that creates our performance bottleneck. It'll be something else. I'm Jacob Brennan. I'm making a new action-adventure game and documenting the process here on YouTube so that you can follow along. In this video, I'm going to show you a tour of my code, focusing on the parts where I use the SDL library for graphics. SDL is a library that sits between your code and the operating system and abstracts away some lower-level functions like drawing and audio so you can focus on the game or whatever other application that you're making. This isn't going to be a tutorial, but if you're trying to do this, you might pick up on something that helps you out. What I will tell you is that there are a couple bugs here. I know of at least 2 in the program that I'm going to show you. If you see any more, please let me know. It'll make the game that much better. And with that being said, let's get to it. To start with some really general, basic stuff, the 2 main tools that I use to program are this code editor and the terminal. When I want to turn my source code into an executable, I type make and it compiles. That happens because I have this make file. The make file works with a program called make, and all this file does is it invokes the CMake program. CMake looks for my source code in the source directory and builds the executable in the build directory. Really simple stuff. With that, we can forget about everything outside of the source directory and take a look at the CMake lists. This file basically does 2 things. It tells the CMake program where the code files are and how you want them linked. Here we have a couple of source files and some subdirectories, like the system subdirectory, for example. There we can see that there's another makelist file with its own set of source files. So it's a hierarchy of files. Helps you to organize things. And that's how I have my program set up, is a series of modules with their own submodules. Every program in C has a main function, and this is where the program starts. Most main functions look basically the same. There's some initialization, some cleanup at the end when the user is done with the program, and in the middle we have a loop. This goes through and handles user events like keyboard and button presses, and then it does something else and displays. This should all look very simple to anybody who's seen a C program before. Where we start to get into graphics specifically and SDL is here where we're including SDL, and then we initialize it. So in order to use it, we have to initialize the SDL system, and then its subsystems. Here we're saying we want video, and we want to be able to capture user events. This is the important one for our purposes, is the video. After that, we're going to set up the client. And that's where we're going to start to configure SDL for our purposes. So let's go into the client subsystem, and we're going to go to client root. This is the function that we were looking at before, client setup. And you can see that there's some SDL-specific function calls here. Then we set up the keyboard, and then we do some of this right here that's not important for what we're talking about today. The important parts are these. First, we're going to create a window that allows us to have a little window that we can drag around. Then we're going to create a texture, which is an SDL-specific thing that you can draw to, essentially. And we're going to give that texture a renderer, which is where our software rendering will take place. We're also going to set its vsync here. That vsync is very important because we want the graphics to only update when the computer's, the monitor's refresh rate happens. So every time the monitor refreshes, we want to update our graphics in sync with that. And if we look back towards our main loop here, you'll notice that there's no sleep at the end. We don't rest, we don't wait. So normally this would cause a very fast endless loop that would eat up our CPU, and you'd hear your fan turn on and it would sound like your computer was going to die. The reason why we can get away with not having a wait in our loop is because this vsync takes care of that wait for us. It inserts that little wait in between the monitor refresh rate. So that takes care of the setup. But where's the actual drawing taking place? If we think about our idea of pixels being drawn to a screen, we might expect to see something like this. An array of pixel data, as large as our resolution, let's say. So here's an array with zeros in it. And then we'd expect maybe we have an SDL function call where we say, draw pixels. We would pass it our pixel data probably. We might even pass it a window, like the main window for our program. We might even pass it some offset, so we're saying where in the window to draw our pixels. So we expect to see something like this somewhere in our program, if that's really how we're going to do the software rendering. If we look through this program, this client, we'll eventually find client display, where we have this pixel buffer, and then this call to draw buffers to VRAM. If we go back to our main loop, we'll see that we actually call this function, client display, in our main loop. What this does, here's our first bug, but we'll get back to that later. This does something here, which we'll also talk about later. Will start to make sense. But then we create a variable that's going to hold our array. It's not an array yet. It's just it will be an array later. It'll be an array once we request that array from the SDL system. So here we're locking the texture and we're saying, please give us an array that represents the pixel data for that texture so that we can then write into it and we can be sure that we're the only people writing into it. We then do that writing here, and then we unlock it. We release that texture for use by others. We update it, we render, and then here's the important part, is the render present. That's, I believe, where the actual sleeping is done. So that every time the computer, the monitor refreshes and wants new graphics, we present it with this render and we say, here's our new data. And after it's done doing that updating, it then sleeps. So now we know we have some pixels and that we sent them to the screen, but what's going on here in draw buffers to VRAM? And what's going on here with driver display root? That's what we're going to talk about next, but first I'm going to mention this modulo 2 right here. This is my way of saying only update 1 out of every 2 times. My monitor runs at 60 frames per second, and I want the game to update at 30 frames per second. If we run this code on your computer that updates at 90 or 120 frames per second, the speed is going to be incorrect. So I need to come back here and update this so that we can determine the speed of the client's monitor and change that modulo operation depending on that speed. So there's one bug. And to do, remember me. I don't remember that, so yeah, there's something important that we've forgotten. That's potential bug number 2. Dear developers, don't write a comment like this. Okay, so what is draw buffers to VRAM? If we try to find that, we're going to find that in our system submodule. This submodule represents a fantasy console. A fantasy console is like an emulator or like Pico 8, where it's a software program pretending to be hardware so that you can write old style video games with the restrictions of that era. Draw buffers to VRAM specifically is in the drawing section. And it looks like, let's see, it looks like this. Nope, it looks like this. So here we're receiving that pixel buffer, and you can see we're actually writing red, green, and blue and full alpha channels, so fully opaque. We're writing those color channels to the pixel data. So here's where we're actually doing the software rendering. This renders the background. This is saying whatever the color of the background is, give me a full screen of just that every time we update. Then it's going to draw some background sprites. So this could be any projectiles or characters that are moving around in the background being behind what are called the screens. So these are going to be tiles, trees, water, grass, houses, that kind of thing. After we draw that, we then draw the foreground sprites. This will of course be your character, your projectiles, monsters, etc. This system of background, color, background, foreground sprites, and screens is essentially copied from the NES. If we look at this function, we'll see that we have this draw graphic and draw screens. And if we look at draw screens, we'll see that it does some things here, and then it also calls draw graphic. So the thing that actually does all the drawing of the graphics is the draw graphics function. It receives, again, the pixel buffer that we're going to write into, but then it also receives a graphics table. If you've done any work with the Nintendo Entertainment System, you'll know what a graphics table is, but it's basically a sprite sheet. It also gets a graphic index, which says which sprite from that sprite sheet to draw, and then a palette, which is what colors to draw that sprite with, and then offset X, offset Y. This is where on the screen you want the sprite, and state is things like, is it mirrored horizontally, is it mirrored vertically, etc. It does some math here to determine, is it outside the bounds of the screen? We don't want to be writing to data that we can't access. That would be a seg fault. And then here, we essentially determine the pixel value from the array of numbers, which is the graphic. Then down here, we write it into VRAM. So at a very basic level, that's how drawing is done in our program. That's how we actually get from a pixel buffer to images on the screen. But that doesn't explain how our program actually uses those sprites and uses those tiles. Let's look at that. First, we're going to look at the sprite data. Anything in the program can request a sprite, and it gets back one of these sprite structures that tells us what graphic we want to use for the sprite, what colors to display, and where it is on the screen. We can also look at that screen object, which is just a grid of graphics indexes and palettes. So basically your background screen is just a big grid, and when you want to change that, you call screen grid set and screen palette set. And that's essentially how the game runs, is that everything in the game is either requesting and drawing sprites or is modifying the tile grid. But let's look at how that's used in the game. So when the game wants to draw something, it calls this client display, and then here was that function that we saw earlier that I said we'd get back to, driver root display. What this accesses is basically a hierarchy of these things that I've called drivers. And they all have a display function, and they all have a couple other functions that are useful. Let's take a look at one of them. Here's the title screen. Whenever we want to draw the title screen, we call this function. And technically this function is not as optimized as it should be. We don't need to set the palette and draw the background every time. So let's move that up here to focused. Focused is called whenever we say, okay, we're on the title screen. So we're going to focus on the title screen, and that's going to set the background color. It'll set the palettes, and it'll draw some text. Now in the actual display, all we need to do is blank out all the sprites, so basically erase all the sprites, and then we're going to request a new sprite called the cursor. And we're going to give it a graphic, give it a color, And we're going to set its X and Y based on where the user has placed their cursor, so what option they've selected. If we take a look at another of these drivers, like the gameplay driver, I actually don't know what we're going to see in this, so this is going to be a little interesting to me. Okay, all that we're doing in the gameplay driver is we are drawing the actors. These are basically monsters and the player and projectiles. So for every one of those that exist in the game, we're going to request some sprites and draw that actor. That's what this actor draw function does. In fact, if we look at one of the actor draw functions from within our game, we don't have a lot of actors at the moment, but let's look at the hero. If we look at their draw function, you see that there's a lot of sprite requesting. We then set the palette and the state of the sprite, and then we set things like their X and Y position, depending on which direction they're moving, are they attacking, etc. So that's essentially how you create a video game without a commercial game engine, is that you make your own. In my case, I have a concept of the fantasy console or the system that has sprites and tiles, and anything that wants to get drawn in the game can request a sprite, or it can modify the tile grid, and then as the user's monitor refreshes, it'll just draw out that data as pixels. If you like this, please like, share, subscribe, ring the bell, do all those things, and you can watch as the game comes together. I'm also going to open up a Patreon so that you can, if you are my patron, you'll get access to early builds of the game. So if you want to have that real backstage experience of seeing the game as it's being developed, consider becoming my Patreon. It would mean a lot to me. And I'll see you next time.